So I'm Selen from the University of Minnesota, and I'm gonna talk about our work, fingerprinting keywords in search queries over Tor. And this is a joint work with Shuai Li and Nicholas Hopper from the University of Minnesota. So our study started from the privacy concern in search queries. So people usually use search engines to search their interests. So in other words, the search queries contain a huge amount of personal information. So as we already know, the AOL search leaks is a good example, so which reveals the sensitive information about users, such as the medical conditions and political leanings, and so on. Therefore, the information leakage in search queries should be, non-trivial private threat. Then, how can you protect the user anonymity in search queries? So one possibility is to use Tor, so to hide the link between the user identities and their search queries. But as we already knew, right? So even Tor does not completely hide, the user browser activities, so which has been intensively explored by website fingerprinting research. So I think we had already good introduction what it is from previous two slides. So to just briefly speak, so if there is a network adversary who can observe the communication between the Tor entry guard and the client, then the collected network traffic discloses a reasonable amount of the traffic pattern to identify which website the user has visited. Then can you fingerprint the search query traces which are from a single web server? So here, the Google. Then is this same passive adversary to still able to infer the search query traces which eventually leak the information what keyword the user typed? So our goal here is to how we can extend the existing website fingerprinting techniques for keyword fingerprinting, and how about the feasibility of it in different experimental settings. So at first, we tried to use the most recent website fingerprinting features. So actually at that time, it was a QMU classifier, so which was presented by the Panchenko et al. In 2016. And actually we got around 90% of closed-word accuracy, so which is not so good. So after we evaluated our existing classic website fingerprinting features, and we found that the result is not so good. So actually, we are going to show the tables of this result later. So here is so here is the PCA space, which has the web page traces, the widely spread green dots, and Google query traces a tiny dense blue area. So the variation between the Google query traces is very small, so which is not enough to identify the different keywords in the data set. So we decide to find a new data set, so new feature set for keyword fingerprinting. And we collected the keyword traces, almost 250,000 keyword traces. And we considered the different keyword data set, including the top-ranked keywords and blacklisted keywords and AOL search queries. And then we evaluate the keyword fingerprinting in various settings. So for example, we consider the different Tor browser settings in terms of the disabling JavaScript. Also, we consider the different size of monitored and background data set, and so on. So in keyword fingerprinting, we have the three stages. So first, we need to filter out unnecessary web page traffic. So distinguish search result traces of a target search engines. So we explored three different search engines: Google, DuckDuckGo, and Bing. And then the adversary is to determine whether the monitor traffic is in his list or not. So this can be easily done with the binary classification. And the last one, which is more exciting part of this paper, So the adversary tries to infer then what is an actual keyword that user typed. So this can be done by the differentiate between the monitor query traces in the tiny blue dense area in the previous slide. So for new feature sets for keyword fingerprinting, we found that all keyword traces actually include a giant sequence of incoming packets at the end of trace. So we name it the response because we assume that these are for the incoming packets of web embedded object in the document file. And for the remaining part, we call request. So we ran the SVM classifier on these different two portions, and we found that so only focusing on this response portion actually gave us better result. So that is around the 70% for Google and 21% for DuckDuckGo. But those are not enough. So we additionally use the cumulative size of the features in this response portion. So for example, cumulative sizes of the trace records and the number of total cells. Also, we use the total packet statistics in this specific portion. Also, we found that among the classic website fingerprinting features, the total packet statistic has still some power. So we aggregate this feature on our best feature set. So finally, we aggregated the 4 different features, and we name it, so aggregate 4. And then we evaluated different classifiers which are used in the website fingerprinting papers. So we use a QUMU classifier, so which is based on the SVM with the cumulated trace, and the K fingerprinting, which is the random forest with Hamming distance, and KNN classifier. And we found that for keyword fingerprinting, the SVM with the response-based feature sets works better. So we used our SVM classifier with the response-based feature set for all the experiments we have done. Also for the metrics, we used both precision and recall for the binary classification. Also, we used the different label learning. So we used both the binary and the multi-label learning because depending on the attacker's interest on different matrix, we can suggest the different label learnings. And for multi-class classification, we use a different matrix, which is the median monitor accuracy, so which we counted the number of monitor traces which are classified correctly over the total number of the monitor samples. So first of all, for the first stage of our attack, so we can perfectly identify search query traces of a particular search engine, so using QUMU classifier. So for our the three search engines, we got almost 100% of the precision and recall. And then we evaluated our website fingerprinting classic features as well as our response-based features. So as you can see here, the response-based features outperformed other existing, the traditional website fingerprinting features. But still, the total packet statistics of the entire trace leaks some amount of information. So this is the reason why we use this feature for our feature aggregation. And for the binary classification, so with increasing size of background as well as the monitor data set, so the both matrix precision and recall decreases. Also, we use the different label learning. So the left side figure is the binary label learning, and right side is the multi-label learning. So we found that the precision becomes better with the multi-label learning. In contrast, recall becomes better with binary label learning. So actually, we separately reported the other graph by using different C and gamma pairs for the SVM, and we got the same result. So if the attacker is more interested in the precision, then multi-label learning can be recommended. Otherwise, the binary label learning could be the better choice. So similarly, sorry. Yeah, the performance of multi-class classifier is degraded with increasing number of size of monitored and background data set. And, but still we are able to get around 25% to differentiate, the different 300 keyword traces against 80,000 of background traces. Also, we consider the different query settings. So this is whether the JavaScript is enabled or not. So by default, the Tor browser enables the JavaScript. So this can be represented by incremental queries. So all traffic related to the suggestion list returned by the autocomplete of search box, and the search predictions by Google instance can be captured. But when we disable the JavaScript, right, so this can be represented as the one-shot query setting. So we conclude that the performance of multi-class classification for Google is improved with incremental query settings. So the reason is quite obvious. So such additional convenience search functionalities, such as the suggestion list, actually leaks some amount of the traffic pattern for the keyword fingerprinting. Yeah, so disabling JavaScript is very well-known recommendation in security perspective, but also it helps to mitigate the traffic analysis. And also the keyword fingerprinting can be applicable to most search engines because they follow very similar format, so which enable us to construct the response-based feature sets. So also, among the 3 different search engines, we found that the Google is the more vulnerable because the big difference here is Google supports the Google prediction, which is search prediction, which is returned by Google Instant. So which means the search prediction also discloses additional traffic pattern. So I think we have now covered all research questions we had in the experiment, but also we have evaluated keyword fingerprinting under different website fingerprinting defenses, such as the Buffalo and Tamaro. Also, we investigated the factors which impact the fingerprintability of the different keyword traces. So for such remaining research questions, I think please look at the paper. And for the practical deployment, there can be several concerns on this approach. So there might be the caching and location and time effect on search results, which means we might get the different search results depending on these different factors. So for the caching, actually by default, Tor browser disabled caching and cookie between the browser sessions. So we assume that always same content is returned to different users if they type the same keyword. Also for the location effect, so we closely looked at the Tor log, and we found that during the capture, exit nodes were selected among the 43 different countries. So we thought that the location effect is already reflected in our data set. Also for the mitigation, actually we evaluated keyword fingerprinting under different website fingerprinting defenses. So still, padding-based serology also degrades the keyword fingerprinting, but at the cost of a huge amount of the bandwidth. So I think, so for conclusion, so we introduced the new application of traffic analysis, which is a keyword fingerprinting, and we investigated the different feature sets using the statistical method. So actually, we used the Kruskal-Wallis H-test. So for details, you can check it in the paper. And we also analyze what kinds of variations we should consider for this new application. So for example, different search engines and different total browser settings. So this is the end of the slides. So I will take any questions.
Yes, let's thank our speaker first. Great.